So greetings. So welcome to today's class. Just to quickly recap where we were last class, we were looking at performance, right? So we were looking at the fact that when we analyze dynamic systems, one looks at both stability and performance. As far as our notion of stability at the time being, we were looking at before stability. And as far as performance is concerned, by and large in this domain, what happens is that when we talk about performance, we talk about metrics which are derived from the step response of first order and second order systems. So in the previous class, we looked at first order systems. We considered the typical governing equations of first order systems, and then we derive the transfer function, identified what is called as a type constant, saw what its definition is and what the consequence of the type constant is, and based on that, how we can get settling time to be 4 times the time constant. Okay, and we also looked at variance of first order system, including the one with time delay and how it can be approximated, right? So that's where we stopped in yesterday's class, right? So in today's class, we will let's build on where we left off, and let's start looking at what are called second order systems. Okay, so once again, just like first order systems, the step response of second order systems is used to derive parameters, that are indicative of the performance metrics, of dynamic systems. We'll see what these are and what metrics we get from this analysis. Okay, so typically these second order systems, let me first write down the general governing equation. So the general governing equation of a second order linear time invariant single input, single output causal dynamic system. Of course, I'm not writing all those objectives. It's understood that that's what we refer to when we write the word system in this particular course, unless otherwise stated explicitly. So the general governing equation of the second order system that we would be considering, right? Considering is given by, right? So there can be other variants, but what we will consider is the following. So we will consider y double dot t plus 2 zeta omega n y of t plus omega n squared y of t is equal to omega n squared u of t. Okay, so this is the generic form that we would be considering. So one may wonder, hey, how come suddenly we are writing, specific coefficients, and what are these symbols zeta, omega, n, and so on, right? So it so turns out that, as I always mentioned, this dynamic systems and controls, it's truly a multidisciplinary field, right? We have looked at influence of electrical engineering, chemical engineering, and so on, right? And this standard second order equation is now motivated from mechanical engineering. Okay, so this is motivated from mechanical vibration problems. Okay, so that's how we take the standard equation. So this is more motivated from vibration problems in mechanical sciences. But before we go further and I explain what these parameters are, and anyway, we figure out the physical meaning of these parameters and their usefulness in the context of our discussion of vehicle dynamics as we go along. In fact, we are going to see a lot of application. Please remember all this analysis very carefully, because when we go and analyze, for example, cornering response, suspension response, and so on, we will be revisiting this class of equations. Okay, so not only the first order but also the second order systems. So the reason why it's called second order, as we already know, the value of n is 2, right? Because on the right, what to say, left hand side, the highest order of the output is 2. Okay. Of course, we have written the parameters or coefficients that multiply. Oh, sorry, here I'm sorry about this. Please make this change. This should be y dot. Okay, the second term. I missed putting a dot over y. So it's 2 zeta omega n y dot. Okay. So essentially, the coefficient of y dot is 2 zeta omega n, and the coefficient multiplying y is omega n squared. The reason why we are taking in this specific format, as I mentioned, it's due to the fact that this equation is motivated from vibration problems. And similarly, on the right-hand side, the input u of t is multiplied by this parameter omega n squared, right? So what are these parameters? This parameter zeta is what is called as the damping ratio of the system. Okay, so we'll see what this is as we go along. Okay, and like the parameter omega n is what is called as a natural frequency, okay, of the system. So the damping ratio comes in because like there is some damping or friction of associated with the corresponding phenomenon. Okay, and we will see also what is meant by the natural frequency as we go. Okay. Yeah. So right now let's start doing the standard analysis as we know it. So what do we do? First we get the transfer function. Right. So in order to get the transfer function, let's apply the Laplace transform on both sides. Okay, so that's the first step we do. So we apply the Laplace transform on both sides of this equation. So what do we get? We get s squared y of s minus sy0 minus y dot 0. Okay, so that's what will happen to the Laplace transform of y double dot plus 2 zeta omega n y dot. The Laplace of y dot will be s times y of s minus y0. Okay, plus like omega n squared y of s. That's going to be equal to omega n squared u of s. Okay, so that's what happens. Okay, so this. So, and in order to get the transfer function, what do? We substitute all the initial conditions to be 0, right? So y0 would be 0, y dot 0 would be 0, and so on, right? So we substitute all the initial conditions to be 0. By now, all of us are familiar with this process, right? So we consider or take all initial conditions to be 0. Once we do that, we have to substitute y0 is 0 and y dot 0 as 0. So once we are to complete this step, what's going to happen is that we will get s squared plus 2 zeta omega n s plus omega n squared times capital Y of s is going to be equal to omega n squared times u of s, right? So this is what. Okay. So then what happens is that if we cross multiply the Planck transfer function, which will be the Laplace of the output variable to the Laplace of the input variable, will be essentially omega n squared divided by s squared plus 2 zeta omega n s plus omega n. Okay, so this is what we. Okay, as the transfer function for this standard second order system. Okay, so that's what we are going to be ending up. So now, so once again, see, by now I'm sure all of us know the process, right? So we also sort of have got a what to say this one, right? That we essentially write down certain characteristics or properties associated with transfer function and do the analysis, right? So what do? First, we identify the values of n and m, right? So the value of n is 2, the value of m is 0, right? So that's what. So consequently, there are no zeros. Okay, the numerator is only omega n squared, so there is no polynomial of s in the numerator, so there are no zeros. And if you look at the poles are going to be essentially the roots of this equation, right? So how do I get the poles? I essentially solve the denominator polynomial to be equal to 0, right? In the denominator polynomial, in this case, is of order 2. And consequently, if I solve it, I'm going to get 2 roots, right? So how do I get the roots? all of us are familiar with solving second order equations, right? Or quadratic polynomials, right? So if I have in general a quadratic polynomial of this form, right? A squared plus bs plus c, and I want to calculate its roots. I solve the equation a squared plus bs plus c equal to 0. And if I write down the roots of this equation, I'm going to get minus b plus or minus square root of b squared minus 4ac divided by 2a. Right, so that would be the solution of this particular second order equation, right? So we use the same method. So essentially, if I use this formula for the roots, the poles will come out to be, in this particular case, the value of the coefficient A is 1, B is minus 2 zeta omega n, and C is omega n squared. Right? So I just substitute. So I will have minus 2 zeta omega n, which is minus B, plus or minus square root of b squared is going to be equal to 2 zeta omega n square minus 4ac, right? So if I write that, I'm going to get minus 4 omega square, right? So that's what I, okay? And this whole thing divided by 2. Okay, so if I simplify this by cancelling 2 in the numerator and the denominator, I'm going to get the 2 poles as minus zeta omega n plus or minus square root of, so if I simplify this, sorry about that. If I simplify this, I get omega n squared out of the square root. I will get omega n square root of zeta squared minus 1. Okay, so these will be the 2 poles of this particular transfer function. Okay, so I hope it's clear how we obtain the poles of this transfer function of the second order system. All right, so that's what we can use. All right. So now the point is the following, right? So if I have to essentially look at first stability, like as we always keep on repeating in the domain of dynamic systems, the first and paramount is stability. Okay, then comes performance, right? So even in the case of first order systems, we figured out that the system is stable because the time constant capital T was positive, right? So that essentially ensured that. Okay. So essentially, we can we have to figure out when under what conditions, right? So this second order system will be stable, right? So it so turns out that the system will be stable when zeta is greater than 0 and omega n is greater than 0. Okay, so as parameters. Of course, one may say, hey, look, this is obvious, right? So when I look at it as a mechanical vibration problems, obviously when I associate a practical meaning with the 2 parameters, zeta and omega n, zeta being the damping ratio and omega n being the natural frequency, I would expect them to be positive, right? So obvious, right? But even otherwise, if we take any general problem where zeta and omega n can be looked at as some real numbers, it so turns out that, if zeta is greater than 0 and omega n is greater than 0, in fact, the system is stable. Okay, so this is sufficient. Okay, so at this point, I just wanted to also draw your attention to an important concept. Okay, so let me take a small detour and then we'll come back to the second order system. But of course, the note which I'm going to describe is also related to second order system. Okay, so a second order polynomial given by, let's say we write some d of s. Okay, so any second order polynomial d of s, which is written as a squared plus bs plus c would be called Hurwitz. Okay, so we'll see, I will define what is this Hurwitz polynomial. Okay, so let me define when we call a polynomial as Hurwitz. So a polynomial is said to be Hurwitz when it has all its roots in the left of them. Okay, so that's when it's called as Hurwitz polynomial. So in other words, a Hurwitz polynomial is a polynomial that has all its roots in the left of complex. Okay, so that's when it's called as Hurwitz. Okay, so a second order polynomial d of s a squared plus bs plus c would be Hurwitz if and only if, okay, all the three coefficients, okay, a, b, and c, okay, are non-zero and of the same sign. Okay, so this is an important result. Please remember, as far as second order polynomials is concerned. And why is it important for us? Because this is important for us when we talk about stability, right? So essentially, if you want the systems to be stable, all the poles of the transfer function must be in the left of complex plane, right? In other words, the denominator polynomial must be Hurwitz, right? Why? Because the roots of the denominator polynomial are the poles. So if I want the denominator polynomial to be Hurwitz, and if the denominator polynomial is of order 2, the necessary and sufficient condition for it to be Hurwitz is that like all the coefficients, three coefficients of the second order polynomial be non-zero and of the same sign. Okay, so that is what we require. That's about it. Okay, so if we look at in our particular case, right? So in this particular case, okay, what we are dealing with second order systems, okay, if we compare it with what we have been writing, right? So if you look at the Planck transfer function, the denominator polynomial is s squared plus 2 zeta omega n s plus omega n squared, right? So the parameter a is 1, so it's positive. B is 2 zeta omega n, okay? And C is omega n squared. So anyway, omega n squared is going to be positive, right? So you take a square of a real number, you will always get a positive number as long as the real number is non-zero, right? Yeah. So A is plus 1, C is also positive. So B should be positive, right? For the two poles to be in the left of complex. Okay. So if I want B to be positive, zeta omega n should be positive, right? So that can mean two things. Zeta and omega n both should be positive, or zeta omega n both can be negative. So both being negative means these zeta omega n are in general some fictitious system parameters. But in our case, since it is we are dealing with a second order system that is motivated from vibration problems, like we know that zeta is positive and omega n is positive, right? So consequently, we are assured that B is going to be positive, right? So so that's why like we wrote down that for stability it is enough if zeta is greater than 0 and omega n is greater than 0, right? So please note that if they have fictitious parameters which are real numbers, zeta less than 0 and omega n less than 0 also will assume stability. Okay, so please note. Okay, all right. So now, having established this, let's come back to our discussion, right, for the second order system. So we have established when it will be stable. So anyway, when zeta is greater than 0 and omega n is greater than 0, the system is stable. However, the nature of the poles and consequently the nature of the system response, right, depends on the value of zeta. So what do I mean by that? Please note that zeta, if you look at the poles, right? So the poles are at minus zeta omega n plus or minus omega n times square root of zeta squared minus 1. Okay, so that's where the poles are. Okay, so now one can observe that in the second term of this pole, we have a square root of zeta squared minus 1, right? So depending on the value of zeta, like the range of values of zeta, we are essentially going to have different types of responses, right? So let us look at what these different types of responses are. Okay, so I hope this is clear to you, right? So let us first consider the case where zeta, the parameter zeta, is between 0 and 1. Okay, so essentially the parameter zeta is between 0 and 1 numerically. So consequently, what will happen? Zeta squared minus 1 will become negative. And then we are going to take a square root of a negative number. So the poles will become complex conjugate, right? So when zeta is between 0 and 1, we are going to get complex conjugate poles. Because, sorry, this is because zeta squared minus 1 is now negative, right? So it's a negative number and we are taking the square root of a negative number. So we are going to get a complex pole, right? And it's going to be complex conjugate. Okay. So if we look at the poles now, let's write down the same poles, but in a different way. So what will be the poles? It will be minus zeta omega n plus or minus omega n times square root of zeta squared minus. See, how are the two poles? Minus zeta omega n plus or square root of, sorry, omega n times square root of zeta squared minus 1 is one pole. Minus zeta omega n minus omega n times square root of zeta squared minus 1 is another, right? So these are the two poles. Okay. So now when zeta is between 0 and 1, the zeta squared minus 1 is going to be negative. So what is the consequence, right? So if you look at this, so I can rewrite this as minus zeta of omega n plus or minus j times omega n times square root of 1 minus zeta square. Okay, so essentially what happens is that I flip the sign in the square root, right? So instead of zeta squared minus 1, now I write 1 minus zeta squared. But where will the minus 1 go? I take square root of minus 1, that is j, right? So that's how we can see that we are going to have a pair of complex conjugate roots. Okay, so that's what will happen when we have zeta to be less than 1. Okay, so consequently, this class of second order systems where we are having uh, complex conjugate poles, right, in the left of plane are what are called as underdamped second order systems. Okay, so and we will shortly notice that they are going to be fast, but then like they are going to have oscillatory response. Okay, so when we analyze the step response of such underdamped second order systems going forward, we will realize that such systems are fast in responding, but then like they will have oscillatory response. Anyway, we look at this data. Okay, so I'm preemptively sharing this. Okay, so let's plot and then like figure out how the poles look like, right, on the S. So let us say I plot the S plane, the real axis and the imaginary axis. Of course, whenever we talk about performance, please note that the premise is always a stable system, right? Only then our discussion makes sense, right? So what happens? Our poles are in the left of complex plane, and there are two poles, and they are complex conjugates, right? So the real part is minus zeta omega, right? So that's what we have determined. The imaginary part is the following, okay? So this quantity omega n times square root of 1 minus zeta squared is defined as omega d, which is what is called as the damped natural frequency. Okay, we will see why it's called as the damped natural frequency later on, but this is the definition. So this is what is called as the damped natural frequency. So consequently, the complex part of the pole are at j omega d and minus j omega. Okay, so I hope this is clear. Okay, the two poles are at minus zeta omega n plus or minus j omega. Okay, so this is what happens. Okay, so now let's what to say to introduce a few more terms. So let us say now I draw the line segment from the origin to one of the poles. Okay, and let us say I call this angle as beta. Okay, so let me zoom into this particular triangle. Okay, and then let me draw it separate. Okay, so this is a right angle triangle. Okay, so let me draw this. So this is my angle beta, okay, which I have drawn, and this end is one of the poles, right? One of the poles. So this base part, right, or the adjacent side, the length of that is going to be zeta omega. Okay, now I'm not looking at the sign, but I'm only looking at the magnitude of the triangle side, right? And this height or the vertical part is going to be omega t, right? Now this is a right angle triangle, right? Is it not? This hypotenuse is going to be equal to, if I use the Pythagoras theorem, I am going to have zeta omega n a whole square plus omega d square. Now, if I simplify this, I'm going to get zeta squared omega n squared, and omega d squared is going to be equal to omega n squared times 1 minus zeta squared, right? So the square root goes away. So if you simplify this, you will see that, I think, oh, no, wait a minute. Yeah, it is correct, right? So this is correct. So if I simplify this, I will get omega n. So the hypotenuse is going to be omega n, right? So I hope all of us can agree to it, right? So this is something which is important. So now, having done this, we can immediately see some important relationships, right? So we will be using these things later on. That's why I'm writing these things on. Please remember them. Okay. So tan beta, as we already know, tangent of the angle is going to be opposite divided by the adjacent side. Okay? The opposite side is omega d. The adjacent side is zeta omega n. And omega d is anyway omega n times square root of 1 minus zeta square, right? So we will write it as omega n times square root of 1 minus zeta square divided by zeta, zeta omega n, right? So omega n and omega n will get cancelled. So consequently, I will have tan beta to be equal to square root of 1 minus zeta square by z. Okay, so please remember this. Okay, so we'll be using this later on. Okay, so the tangent of this angle is going to be square root of 1 minus zeta squared by zeta. Okay, so I hope this thing is clear. And so once again, to just recap, the poles of this so-called underdamped second order system will be at minus zeta omega n plus or minus j omega d. So we are going to have complex conjugates, right? So there are two poles, and these are complex conjugates of one, right? And from the same triangle, if I want to write cos beta, right? See, what is cos beta? Cos beta is adjacent side by hypotenuse, right? For a right angle triangle. So the adjacent side is zeta omega n. The hypotenuse is omega n. So omega n and omega n cancel off. So I'll get zeta. So this is also something which is important. So please remember this. Cos of this angle beta, which essentially is the angle drawn from the origin to any one of the two poles of the underdamped second order system, measured from the negative real axis. So that's going to be equal to zeta. So this is a very important relationship between the model parameter zeta and this geometric parameter beta. Okay, so we have had a sort of like a visualization of the two poles on the S-plane. And what we are saying is that like, this cosine of this angle beta is that parameter. All right, so that's what. Okay, so any questions till now?
Sir, the second order equation which you have assumed, is it a spring mass damper system equation?
So we can correlate it to a spring mass damper system, right? So let's do that, right? So suppose let me write here, right? So let's take a different color. So let's say we write down the mass spring damper system, right? So mx double dot plus cx dot plus kxt k. I'm suppressing that function of time, right? Okay. I hope it is understood that x and f are functions of time. So let us say I write like this. I can rewrite this as x double dot is equal to c by m x dot plus k by m x plus 1 by m f, right? So is it not? Okay. So if I compare the coefficients on the left-hand side, I will have 2 zeta omega n to be C by M, omega n squared to be equal to K by M. So we get very well-known relationships, right? For the mass spin damper system, where the natural frequency is square root of K by M, right? And
Yes,
the
sir.
damping ratio, if you simplify this expression, we will get the C by 2 square root of MK. Okay, so this is what. Okay, so if you simplify that equation, right? So these are the well-known what to say equations, right? So that we know for a mass spin damper system. So you can see the correlation. Of course, one may immediately ask, hey, should the coefficient of the input be not omega n square? So should I not get K by M times F on the right hand side? Okay, the answer is not necessary. You know, like I was about to explain why we have omega n squared multiplying U in the next class where we derive the unit step response. We have this omega n squared in the right hand side to make the steady state value of the unit step response of the standard system to be 1. But anyway, that is not necessary, you know, because we are dealing with linear systems, right? So I give U, I give K times U, right? If I know Y is the output for U, I know that for K times U, K times Y is the output. So it hardly matters, okay? So that is why we are, what to say, comparing the left-hand side and deriving these equations. The last information which I shared about that parameter multiplying U, you will understand it better when we essentially do the what to say this one, right? So when we essentially do the unit step response and associated forces. Okay, so I hope this is clear. Right? So,
Yes, sir. Thank you.
all right. So any other questions before we go ahead? Okay. So let's go. Okay. So now the second class of systems. So we consider the first the range when zeta was between 0 and 1. The second class is when zeta is exactly equal to. Okay. So when zeta is exactly equal to, what happens is that like we have in the if you look at the poles, right? We have minus zeta omega n plus or minus omega n times square root of zeta square minus 1, right? So these are the two poles, right? So this is what gives us the poles. Now when zeta is exactly equal to 1, zeta square minus 1 becomes 0, right? So the second part vanishes, right? So and the first part, which is minus zeta omega n, which just becomes omega n, right? So what happens is that like when we have zeta equal to 1, we have two repeating poles at minus omega. Okay, so this is what happens. All right. So this is what is called as a critically damped second order system. Okay, when the damping ratio is exactly equal to 1, okay, we get what is called as a critically damped second order system. All right. So that is the definition of a critically damped system. And if we look at the denominator polynomial, consequently, we get s squared plus 2 omega n s plus omega n squared equal to 0. Okay, when zeta is equal to 1. Okay, because you remember the denominator polynomial, right? It was s squared plus 2 zeta omega n s plus omega n squared. When you substitute zeta is equal to 1, the denominator polynomial becomes s squared plus 2 omega n s plus omega n squared, right? So consequently, you can see that this is a perfect square, right? So we will have s plus 1 omega n whole square. Okay, that is why we get the poles to be repeated. Okay, and minus omega n. So this is a pair of repeating poles on the negative real axis. Okay, so that's how they are. So okay, let me erase this and write it a little bit bigger. So we have the poles to be equal to minus omega n and minus. Okay, so there are two repeating poles. Okay, so once again, when we have what is called as a critically damped system, we have repeating poles at minus 1. Right, so this is a critically damped second order system. So let me draw the S plane. So I draw the S plane. So in the case of critically damped systems, I am going to have two poles at the same location, -1. Okay, so that's why I've drawn two crosses at the same. Okay. So now going to the next case when zeta is greater than 1. Okay, so we have considered what happens when zeta is greater than 0 but is less than 1. We have considered the case when zeta is exactly equal to 1. Now we consider the case when zeta is greater than 1. Now the poles are anyway at minus zeta omega n plus or minus omega n times square root of zeta squared minus 1, right? So zeta squared minus 1 anyway is greater than 0 now. So these will be the two poles. So we are going to have two poles on the negative real axis. So if I draw the two poles, okay, for this particular case, right? So they will be somewhere here, right? So this pole is going to be minus zeta omega n minus omega n times square root of zeta squared minus 1, right? It's going to be more negative. This is going to be closer to the imaginary axis. This is going to be minus zeta omega n plus omega n times square root of zeta squared minus 1. But it will still be in the left half plane. Okay, it will be on the negative real axis so that the system is stable. Okay, so such a system where we have two distinct poles on the negative real axis, such second order systems are what are called as over damped second order systems. So this is what is called as an over damped and second order system. And if we will shortly see that the response of such systems is going to be sluggish. Okay, so it's going to be pretty slow in response. Okay, so the main feature is that they have two distinct poles on the negative real axis. Okay, so that is the main feature. Okay, so this is the third class, right? So this is what is called as the overdamped second order system. Now, when we consider an overdamped second order system, this pole at minus zeta omega n plus omega n times square root of minus zeta squared minus 1 is what is called as a dominant pole. So what is this dominant pole? Okay, so let me write down the notion of dominant poles, then we will come back and see what they are and what influence they have, right? So what is this dominant pole or dominant poles? So dominant poles are those which are closest to the j omega axis and consequently will dominate the dynamic response of the system. Okay, so in the case of the overdamped second order system, we can see that this is the pole which is closest to the imaginary axis, right? Minus zeta omega n plus omega n times square root of zeta squared. That's why we have marked it as the dominant. Okay, so dominant poles are those, okay, that are closest to the j omega axis or the imaginary axis, and consequently dominate the system response. Okay, so that's what. All right, so they are the poles which are closest to the j omega axis, and obviously they will dominate the system response, right? So what do I mean by that? Let's say we consider an example, right? So let's say there are two poles, right? One at -1 and one at -10. Okay, as an example. Okay, so by now we know that, like when we consider the responses, we are going to get exponential terms with where the what to say, exponents are going to be the poles, right? So e power minus 10t and e power minus t will appear in the output function y of t, right? So so consequently, if you look at e power minus t and e power minus 10t, we can observe that both of them would go to 0, right? As t tends to infinity, right? There is no doubt about it. But then which will go to 0 faster, e power minus t or e power minus 10t?
E to the power minus 10t.
E power minus 10t, right? Larger the negative exponent, faster would it go to 0, right? So consequently, you would observe that e power minus t would dominate the output function for a longer time. I'm sure all of us can agree to that fact, right? So essentially, the influence of e power minus t is going to be felt for a longer time on the output than e power minus 10. Okay, so that is why these poles are what are called as dominant. So for example, let us say we have poles like this. Okay, just some arbitrary system, right? So we can see that these are the two poles that are closest to the imaginary axis, right? So they will be the dominant poles. Okay, so these will be the dominant. So dominant poles can be complex conjugates or they can lie on the real axis. Okay, no problem. Okay, but you get the point, right? Why they are called dominant? Because they are going to be dominating the system's dynamic response for the longest possible time, right? When compared to all the poles. All right, so that is why they are called dominant poles. Okay, and it so turns out that even if you have higher order systems, okay, in real life, the dominant dynamics can be approximated as a first order or a second order system. Okay, so that is why we essentially always look at the response of first order and second order systems to come up with performance metrics. Okay, it makes sense for us to do. And now, so in today's class, just to summarize, we have once again looked at performance. Like we have now considered second order systems. So this is a standard equation of a second order system. So the transfer function is omega n squared by s squared plus 2 zeta omega n s plus omega n squared. The poles are minus zeta omega n plus omega n times square root of zeta squared minus 1. And based on the value of zeta, we are going to have three types of second order system, right? When zeta is between 0 and 1, we have what are called underdamped second order systems. We have complex conjugate poles. And the feature of this class of systems is that they are going to result in oscillatory response, although the response will be fast. Okay. And by and large, designers would go for such systems. Okay. So let me write it down shortly. If we don't want oscillations, but we want the fastest possible response, we go for critically damped second order systems where zeta is exactly equal. Difficult to achieve in practice because if I always want to control zeta to be exactly equal to, right, may not be possible, right? So, but then that's the best possible option if we don't want any oscillations. When zeta is greater than 1, we have what are called underdamped second order systems where there are two distinct poles on the negative real axis, but the response is very sluggish. Okay, so that's when we call it as an overdamped, sorry, zeta greater than 1 is what is called as an overdamped second order system. And we introduce the notion of dominant poles, right? Those which are closest to the imaginary axis and consequently will dominate the response for a longer period of time. All right. So these are the important concepts that we want to learn today. And by and large, when we design such dynamic second order systems, we typically, this is a rule of thumb, okay? That's nothing set in stone. But by and large, like people tend to design underdamped second order systems where the damping ratio is between around 0.4 to 0.8. Okay, so this is just the rule of thumb. Okay, so once again, nothing set in stone. Okay, so we don't want to go too low a damping ratio because then there will be a lot of oscillations. Okay, and we don't want to essentially go too high a damping ratio, right? But then what will happen is that the response will become completely sluggish, right? So that's why we have a range, right? So we will, the next class, when we derive some performance metrics, we will see all these facts also through equations. Okay. So in the next class, we will stop here. In the next class, what I will do is that I will derive the unit step response of underdamped second order systems and use that to derive some performance metrics that will be used for quantifying performance of second order systems. Okay, so that's the exercise we'll do in the next. All right. So are there any questions about what we learned today? All right. So if not, let me stop the recording.